Welcome, everyone. If you're just joining us, a quick reminder that you can submit questions using the Questions tab at the top of your screen. We'll take as many questions as we can at the end of the presentation. And if we don't get to your question, don't hesitate to send it to webinar@neo4j.com, and we'll be sure to have someone follow up with you. Post about today's event using hashtag Neo4j, and you'll be entered to win a cool Neo4j t-shirt. And now here's Lance Walter to introduce our next session, Using Graphs to Enable National Scale Analytics.
David Bader is a distinguished professor and director of the Institute for Data Science at New Jersey Institute of Technology. Dr. Bader has many years of experience in data science and analytics, both in his current role as well as in a 14-year run at the Georgia Institute of Technology. His corporate experience includes 6 years as chief data scientist for Iconic Security. Dr. Bader holds a bachelor's degree in computer engineering from Lehigh University and a PhD in electrical and computer engineering from University of Maryland. Dr. Bader has some really unique insights to share with us about analytics at scale, and I've been looking forward to seeing this talk since I saw the original submission. So let's dive in. Welcome, Dr. Bader.
Thank you, Lance, for that great introduction. Really glad to be here today at Connections with Neo4j, talking about using graphs to enable nation-scale analytics. My contact information is on the slide, and I'd love to tell you some stories about the work that we've been doing. I'm a distinguished professor of computer science at New Jersey Institute of Technology, where I direct the brand new Institute for Data Science. We do a lot of work on big data science problems, from machine learning all the way through graph analytics. And I'm glad to be here today to tell you a little bit about the work that we've done in solving real-world challenges that come from a variety of domains. So often we work in areas such as urban sustainability. How do we have a better day as we go through our lives in urban environments with traffic, having resilient power supplies, clean air and water, food safety, all of these issues in urban sustainability. For healthcare analytics, we try to understand how to have personalized medicine and use healthcare data to make populations more understanding and aware of their medical conditions and best treatments for them. We know that we're in an election cycle, so often we use analytics to secure our elections, to have trustworthy, free and fair elections. Many enterprise companies and even government have insider threat problems where you'd like to detect lone wolves from all of the data at hand. Also, utilities and our infrastructure. I mentioned the power grid, trying to make sure that we have a sustainable power supply and that it isn't under attack. Giving attribution and detecting cyber attacks, and even through full monitoring of the world's disease outbreaks and epidemic and pandemic monitoring. These are the types of problems that are deserving of solutions to make our time on this planet a better place. And one way that we can address these types of problems is using graph analytics, such as the tools provided by Neo4j. Now, it comes as no surprise that our federal government has recognized the importance of data science. In this recent National Intelligence Strategy report, there is mention of this abundance of data providing significant opportunities with new avenues for getting data and providing greater insight. But it also challenges our ability to collect, process, evaluate, and analyze such enormous volumes of data. So often we know that we have many different data sources that we could plug into, and the data is arriving at very fast rates from all different times with different veracities. And we need to be able to respond to that in near real time to make decisions and get insights. There has been a national effort for a number of years, going back to the Obama administration issuing in 2015 the National Strategic Computing Initiative, and this was just updated November 2019 by the current White House for an updated strategy for the nation of how we look at partnerships among academia, companies, and industry for working with the government to solve some of these real data science problems. The National Science Foundation has recognized the importance of the ability to manipulate data and understand data science. And even analysts such as the McKinsey Global Institute has predicted that data-driven technologies will bring an additional $300 billion of value to the US healthcare sector alone. And so on, we're faced with these tremendous data science problems. Again, here is Michael Kratsios, the US Chief Technology Officer, thanking me in a tweet for sharing the news about the update to the National Strategic Computing Initiative that I've had the privilege to be a part of developing this national strategy. So the reality when we talk about data and graphs is we get something like this. This is an old friendship network, a social media network from Friendster many years ago. And it's really a small network by comparison these days. And yet often our data looks like these big messes, these big hairballs, where it's hard to pull out relationships and information, but we'd like to take all these different types of data and really get important insights out of them. So this is why we move to graph analytics. Often the graph analytics are representing the connectivity information, the metadata, and the relationships between objects, rather than storing all of the raw data. So I can often fit this graph of connections into the main memory of my computer, and I can do very fast responses to different types of important queries, and even do pre-joins of databases that would be infeasible in a relational database. But given a graph database, I can combine these data from different sources and of different types very easily. And as I'll show in a minute, some common intelligence and law enforcement queries are naturally posed on graphs. It's just a natural representation to look at the interplay between different people, places, and things, whether we're looking at people within an organization, parts within a supply chain, or even network traffic going across the internet. So here's an example. This is a shortest path type query where I have vertices or nodes, which are these black circles, and some are colored red, some are blue, and some are black. And those colors are representing the types, such as workplaces, town, people. And then I have different types of edges representing known relationships between those objects. So you may be friends with someone, you may work at a particular location, you may live in a particular city, and on and on. And what we do with this information is we build these graphs, and the graphs can be quite large, and again, tie together different objects with different types of relationships. And in this type of query here, I show a shortest path between two vertices, 13 and 25, that may represent the path of connections between two different people represented by those two vertices at the end. So this is one type of graph query, a short path. Another type may be trying to find patterns or motif finding. Here on the upper left, I have a template or a motif where I have people residing at a house, observing a factory. One is renting a truck, one is buying fertilizer. That may be a pattern that I wish to look for in some larger observed data where I'm looking for something close. And this is often called the problem of subgraph isomorphism, where I'm trying to find a pattern that's very close to that motif. So we call this motif finding, and that's also a very useful graph analytic for looking for information in large graph databases. So again, the big picture is that I often work with analysts, and here we have an analyst on the lower right who wishes to query different types of data. And so it would be a very slow operation to go to traditional massive databases and pull together all of the different types of information that we have, whether it's from newspapers, databases, phone calls, and video, and on, all the different types of data that I may have could be terabytes or more. But what I'd like to do is really pull out that connectivity information. And we see that in the center of this graph, where I take this graph and put it into memory. And then using a graph database like Neo4j, I can make very fast queries. And those queries can happen in near real time on these data sets, and I get my answer much sooner. So that's the great thing about graphs. And often there are different types of queries that we can do with graphs that would be very challenging to do in other types of databases. For instance, I call this the data quad, and on the x-axis, I have objects going from known objects on the left to unknown objects on the right. And on the y-axis, on the bottom, I have known patterns, and on the top, I have unknown patterns. So if I look at this as 4 different quadrants, what I have in the lower left is known objects and known patterns. This is where relational databases have worked for us since the 1980s and done a great job, where we have schema. And you could think of this as having tables. Maybe this represents customers in a store, the products that the store sells, and then shopping carts as customers check out and buy their items. And when we know everything about the data, this works great. Now, the 2 off diagonal on the upper left and the lower right are newer types of queries where, for instance, on the upper left, I have known objects, but I don't know what they're up to. This would be akin to a problem like an insider threat with a large organization, where a person has triggered some alarms, and I want to go and explore and see what they're up to. I want to look at who they're sending email to, what files they're touching, what network access they've had, and really look around to see if it was just an erroneous false positive, or are they really up to some malicious activity. On the lower right was the same subgraph isomorphism or motif finding, where I have a pattern that I'm searching around. And these are places where graph databases do very well. The emerging area is the upper right, that I call exploratory data analysis, or finding the unknown unknowns. Often we are trying to reduce risk or eliminate surprises. And for strategic intelligence, we really have to move to this upper right quadrant to figure out what are the things that we haven't seen before in data sets, and what are those features that are going to really be surprises that we want to find out before they become some egregious event. So graph databases help us move into this 4th quadrant of unknown unknowns, as we're really trying to explore our data sets and really try to figure out what exactly we have. So many real-world challenges involve large graphs, from healthcare, for instance, trying to detect and prevent epidemics and pandemics, as we see now with the global transmission of the novel coronavirus, or understanding massive social networks, understanding how communities form, how they dissipate, how they operate, what their intentions are. How do we look at spread among populations for transportation, evacuation during storms, and on and on. For business intelligence, we want to have analytics, business intelligence analytics, anomaly detection, cybersecurity, knowledge discovery from massive data sets, so that we can monetize the data that we collect from our customers. Systems biology for understanding complex life systems, understanding life itself and disease. I've mentioned the electric power grid that's responsible for communications, transportation, energy, food, water, the water supply, and on. The resilience of that power grid is going to be a very important problem. Again, these are all cases that we could employ graphs to help solve these types of challenges. Even performing full-scale economic, social, political simulations of entire nations requires the use of graphs. Now, graphs come in many different forms, many different shapes and sizes. Here I have a couple graphs. One is from astrophysics on the left. In the middle is a graph from bioinformatics and looking at protein-protein interaction networks. And on the right, I have a social network from a social informatics problem. And all of these are graphs, but they look in different ways. And I often have different challenges with the data sets. So for instance, in that astrophysics problem, I may be looking for temporal variations that lead to the discovery of quasars. And these are massive data sets where I may want to run graph problems like clustering or matching of those objects in the images to do that outlier detection. In the middle, I may have issues and challenges with the data heterogeneity and the quality because much of this data comes from laboratories that may have different processes for doing the protein identification. And the graph problems that I may be trying to run refer to analytics such as centrality and clustering in order to identify drug target proteins. On the right, these are social networks where there are new analytic routines that we're discovering every day to try to understand how emergent communities evolve and how information spreads through networks, where the graph problems that we need to solve relate to clustering, maybe shortest paths, or flows of information through the graph. So these are all real applications, and yet the abstraction of the graph helps us solve these in a similar way using graph databases where we map our application to these graph abstractions. We decide what is a vertex and what is an edge, and then we look at the right graph kernels to run that will solve the problems that we hope to achieve in the real application. So there's many types of graphs. This is a conspiracy theory graph where you could do the same thing. Just don't tell anyone I told you that. Okay, so back to the talk. We have massive data analytics that we could apply to the infrastructure. For instance, this is a map of the US power grid, and there are over 150,000 miles of US high voltage transmission lines. And what we'd like to do is real-time detection of changes and anomalies in the grid. And it's a large-scale problem that we really have to understand the resiliency of this power grid so that we don't have blackouts or other equipment damage or failure in this type of network. Another type of graph that we have comes from intelligence and surveillance. These are some public graphs. The top one refers to the hijackers on September 11th, and it's been argued that if we were able to identify the graph actors, we would have been able to run graph problems like centrality to pick out who were the hijackers on particular planes, and more importantly, who were the masterminds behind the plot. On the bottom is a graph that I've shown before with this Motif finding. This exact or approximate graph matching often gives us a very insightful way to view real collections of raw data. So these types of analyses really get us past what relational databases can supply. And sometimes we use algorithms. For instance, this is some work that I did with my lab where we took a social networking algorithm called betweenist centrality and applied it to the human proteome of all of the protein-protein interactions that have been stored in GenBank. And through this, we were able to find essentially what's like a needle in a haystack, where we looked at the proteins that were not the ones that were most reacting within a cell, but the ones that had importance for the structure of the network using betweenist centrality. And instead, they did not interact with a high number of other proteins. And in fact, the protein with the highest betweenist centrality has been implicated in breast cancer. So this gives us new ideas for ways to delve into a data set where we may not have the right tools for doing understanding, but the graph gives us a way to figure out the structures and really the subtle aspects of individual vertices and nodes within these types of data sets. Often we have problems where there's information coming in near real time rather than just a static data set that we're trying to analyze. And this is what I call streaming graph analytics, where on the left of the slide, you see that you may have people interacting. And here I represent it as tuples. And the first tuple A, comma B, comma T1, comma poke means that person A or object A at time T1 poked person B. And so I can take these types of interactions and form tuples and basically create billions of nodes that I can ingest into my graph. And once I've ingested these, then this graph will change over time as I get these new updates. And I could ask one or more queries into that graph that I keep forming and changing as I get new information. So this is what I mean by streaming or dynamic graphs. It's the ability to change my representation over time and either add new information in or retire old information from the graph as well. Now let me tell you a little bit about centrality, which is a very important network, as I mentioned previously in this talk. It's a quantitative measure to really capture the importance of a person in a social network. It's a global index related to shortest paths that traverse through that person, and it can be used for detecting communities as well. Now, this idea of finding the most central nodes in a large complex network has been found to be a key metric in several applications, ranging from biological networks, and I mentioned the protein-protein interaction networks on a previous slide, or looking at sexual networks and AIDS transmission, identifying key actors in terrorist networks, understanding organizational behavior, managing supply chains, and even looking for congestion in transportation networks. This has been really a workhorse, and it's great that in Neo4j we have these types of metrics easy to use on our graphs. So by definition, betweenist centrality is here's a formula of the betweenist centrality on a vertex. It's really the fraction of the number of shortest paths in the graph that go through a particular vertex at hand. Here in this simple graph that I have, the two vertices colored red would be more important than the other vertices, because if I remove a red vertex, I most disrupt the paths in that graph. So it's really a counting argument of shortest paths, and it turns out to be very useful in many applications. For instance, we decided to look at a breaking event and using the full take of public tweets back about 10 years ago. We were the first group using graphs to take all of the public tweets of Twitter, form a graph out of the followers and followees, and look for breaking events. And at that time, H1N1 virus was a breaking event where people did not know the mortality rate for that pandemic. So you would think that you would tune into a number of different places like the government or commercial media to figure out the information about staying safe with that virus. When we did our analysis, we were able to use graphs and betweenist centrality to pick out some of those important handles. So a ranking of the top 15 users by betweenist centrality are on this table, and we see at the top position the CDC flu handle flu.gov at number 4, CDC emergency, CDC eHealth. So we're able to pick out these official government sources very well for the most importance as to where people are getting information. And we also saw commercial news media. We see the New York Times, we see CNN, Time Magazine, and so on. So we're able to pick those out as well. But the surprise that graphs gave us was something that you would never think of before a breaking pandemic or a breaking event such as this, which is item number 3, so official PACs. So we pondered, what is official PACs? How was this so influential during the spread of H1N1? And it turned out that this is the handle for the penny arcade gamers group, basically a set of adolescent males who at this time were in Seattle at their annual conference. And they were the first group in the United States to get infected with H1N1 and start tweeting with each other, hey, how do you feel? Not so good. Why don't you go to the doctor? Yep, I went to the doctor. How do you feel? Well, it's okay, it feels bad. They confirm that it's H1N1. And then the tweets would go into some of the conditions and symptoms. Is your nose running? Does your throat hurt? And then it moved into questions like, hey, Bob, are you dead? Nope, I'm not dead yet. Peter, are you dead? Nope, not dead yet. And so this is not the group you would have expected to listen to during a breaking event such as H1N1, but it turned out to be some of the best information for staying safe during the H1N1 pandemic a decade ago. So this is the power of graphs, that we can take information that may seemingly be unstructured, we don't know how to analyze it in any other way, and we can use it in near real time to make these decisions or to look for important features within the data set. So to conclude this talk, graph data science is really an important technique for solving real-world grand challenges. Graphs are a natural abstraction for big data and connecting people, places, and things, especially in large organizations and government, where we have massive data sets that really are global in nature, where we're trying to get understanding and meaning. Graphs are a useful technique in problems such as tagging data that we receive and collect, triaging to decide what to do with the data, exploratory data analysis to understand what we're holding within our data sets, even finding anomalies within the data, finding patterns, locating insider threats within large organizations, detecting fraud, and other advanced analytics. These are all just naturally represented by graphs. And technologies such as Neo4j provide the enterprise class performance that we need to solve these important mission problems. So getting started with graph databases is easy, and I encourage you to pick up Neo4j and try to take your data sets and combine them into a graph and start figuring out how you can ask important questions of the data that you have. So with that, I want to thank you for your attention, and I'm here to answer any questions. If you wish to reach out to me, here's some of my contact information on this slide. So thank you very much, and I hope you enjoy the rest of the day in Neo4j Connections.
Wow, thanks, David. That was a really great presentation, and so many great use cases for graph. And I love the Twitter with H1N1. It's just so interesting and seeing the different ways, and especially with packs.
Thank you.
So we have time for a few questions. We have a lot in the Q&A. Let me look right now and find some. Here's a good one. Can graph databases work with data in other data stores?
That's a great question. The graph allows us to federate the information across multiple data stores. So we may, for instance, extract out features of the data that we can then ingest into our graph. So for instance, we may have different types of records where we understand relationships between the records. And we can naturally use graphs then to tie together this great variety of data in the different data stores. So that's a great question, and really one of the powers of graphs is to be able to do exactly that.
Awesome. Alrighty, I think we have time for one more. So let me look right here. Here's a good one. What are some problems that require tracking graph changes over time?
That's a great question. So graph changes give us the ability to really track things in near real time. And often traditional databases are too slow to ingest and be able to make real-time decisions. But with graphs, we may have problems, for instance, in network security, where we want to understand threats to our organization, and we capture the network traffic coming in. And what we would like to do is take updates either every hour, every minute, every second, or even faster, and use that to really change our view of what sessions are connecting between our organization and the rest of the world. So in network defense and network security, that's a great use for graphs. We have other applications as well where, for instance, in healthcare, we may have daily updates of patient records and patient information that we're using to track the spread of different diseases, or maybe understand the correlation, the spatiotemporal correlation, whether there's an outbreak, whether it's a food safety concern like a salmonella outbreak, or whether it's the spread of a common yearly flu, and on. So we often have many real world applications that aren't just static in nature where we're crunching a data set, but where we're getting daily or hourly or even faster updates. So graphs give us that ability to track, to look for changes, and to look for new surprises in those data sets.
Awesome. Well, thank you, David, for a great presentation and for answering those questions. Marilee, I think that's all the time we have for questions. Is there anything else you'd like to discuss?
Thanks, Pat. And thank you, David, so much for that presentation. That was great. And I want to second what Pat had said in that H1N1 example with the gamers on Twitter. That was such a great example. And you're right, like who would have looked to that group for like leading information on what's happening with this virus? So that was great.
Thank you. That's exactly right. Graphs give us the ability to see things that we would never see otherwise.
Exactly. And I want to thank you for your time in joining us today. And for those in the audience, if your question wasn't answered, you can also send an email to webinar@neo4j.com and we'll get you pointed in the right direction. Our next presentation is starting shortly, so stick around and that will begin momentarily. Again, thank you, David. Thank you, Pat.
Thank you so much.